In this video, we're going to explore the nature of gases and several gas laws. Gases are unique in that they are much more affected by their environment than solids or liquids are. When we investigate the various properties of gases, we can see that these properties are dependent upon the pressure, temperature, volume, and the amount of the gas in moles. Pressure is defined as the amount of force pushing down per unit area. In this example, we can see the force of air pushing down on the mercury, which would then cause the mercury to rise up in our measuring device. We can then measure that rise and get a measurement for the amount of pressure pushing down. The pressure of the atmosphere pushing down on the liquid in this example will be proportional to the height of the column and the density of that liquid. Another convenient way to think of pressure is by thinking of it as collisions on the inside of a container. Here we have some sort of container, this being the inside. The particles inside that container, as they are in constant motion, will then collide with the sides of the container. And so we can think of the number of these collisions as being the pressure exerted by the particles inside the container. There are several different units of pressure. One of the more common one is the atmosphere. And so at sea level, we say that we have 1 atmosphere of pressure. Another common unit is millimeters of mercury, derived from the first barometers. 760 millimeters of mercury is equal to 1 atm. Torr is another unit of pressure. You will note that 1 torr equals 1 millimeter of mercury, and so 760 torr is also equal to 1 atm. Pascals are another often used unit. 101,325 pascals are also equal to 1 atm. We quite often think in terms of kilopascals if we're using pascals as our unit of measure. And so any of those conversions that we saw on the previous slide are simply conversion factors like many others that we've used before. And so in this example, we want to convert a pressure of 610 millimeters mercury over to atm. And so we're going to use our conversion factor of 1 atm being equal to 760 millimeters of mercury to find that this is equal to 0.80 atm of pressure. The gas laws that we investigate in this video are going to be the result of the mathematical relationships between the 4 different things that gas properties depend on: the pressure, volume, temperature, and our number of moles. The first one that we're going to look at is known as Boyle's law. Boyle's law investigates the relationship between the pressure and volume of a gas sample, assuming that the temperature and the amount of moles are held constant. We can see here that pressure is inversely proportional to volume. And so let's think about if that makes sense. If we have some container with a certain volume, and we remember that the pressure can be thought of as the number of collisions of particles with the inside of that container, then we can consider what happens if we double the volume of that container. Again, we're assuming temperature and number of moles stay constant, and so as we double the size of our container, it's easy to picture that the number of our collisions is going to be cut in half because we have a much larger area for those collisions to occur upon. And so we say that pressure is inversely proportional to volume. This leads us to our mathematical expression of Boyle's law, which is P1V1 equals P2V2. In Boyle's law calculations, we will often be describing one set of conditions and looking to see what happens to our gas parameters at another set of conditions. And so let's look at an example here. Here we have a sample of nitrogen gas at a pressure of 67.5 millimeters of mercury in a 500 milliliter flask. We want to know what the pressure of that gas will be if we transfer it to a 125 milliliter flask at the same temperature. And so we have our initial set of information. We know that our initial pressure was equal to 67.5 millimeters of mercury, and we know our initial volume was equal to 500 milliliters. We know our second volume at 125 milliliters, and what we're trying to solve for is our new pressure of that system. And so we can set up our Boyle's law relationship, P1V1 equals P2V2. We know that we're solving for P2, that's our unknown. So if we rewrite our equation, P2 is going to be equal to P1V1 all over V2. And then we can simply plug in our numbers. And we find that our new pressure in this 125 milliliter flask is going to be 270 millimeters of mercury. And now we just stop and ask ourselves if this makes sense. In this case, we went from a 500 milliliter flask to a 125 milliliter flask. And so our volume decreased. We said that pressure and volume are inversely proportional to each other, so this would mean that our pressure would have to increase. And in fact, that's what we do see. We went from a pressure of 67.5 millimeters mercury to 270 millimeters mercury. Let's look at another example. Here we have a 500 milliliter soda bottle that is emptied and sealed in Peru at an altitude of 11,400 feet. And we know the pressure there is 475 torr. If we seal the bottle there and return to Portland, where our pressure is approximately 1 atmosphere or 760 torr, we want to know the new volume, assuming that there is no change in temperature. And so, once again, we write out what we know. We have our initial volume of 500 milliliters. We know our initial pressure of 475 torr. And we know our final pressure of 760 torr. And we're tasked with finding our new volume. And so once again, we can set up our Boyle's law relationship. Now, however, we want to solve for V2, and so rewriting this equation to solve for V2 gives us P1V1 all over P2. And now we can just plug in our numbers. And in doing so, we find a new volume of 313 milliliters. Now again, it pays to take a few seconds to think about if our answer makes sense. In this case, we were going from an area of lower pressure to an area of higher pressure, and so our pressure is increasing, which means that our volume, according to Boyle's law, would have to decrease. And that, in fact, is what we see. We go from 500 milliliters down to 313. Also note that with Boyle's law calculations, you can use any units of volume or pressure that you want, as long as you are consistent. In this case, we began with a volume with the units of milliliters, which means that our final volume that we solve for will also have units of milliliters. Likewise, as long as both of our pressures are in torr, that is fine. If we were given one pressure in ATM and one pressure in torr, we would have to solve one or the other and convert it over so that our units were consistent. The next relationship we're going to look at is known as Charles's law. Charles's law involves the relationship between volume and temperature, assuming that our pressure is going to remain constant. Again, let's think of our fictional balloon. If we have a balloon of a certain volume to begin with, and our pressure involves a certain number of collisions on the side of that container, if we then increase our temperature, so we have to remember that temperature is a measure of the average kinetic energy of the particles. In this case, we can think of it as the motion of those particles. And so if we increase the motion of the particles, in order for our pressure to remain constant, in order for those number of collisions to remain constant compared to what they were, our volume has to increase so that these number of collisions stay constant when they are at a higher energy and have more motion. And so it just makes sense then that volume and temperature are going to be directly proportional to each other as long as pressure stays constant. It is important to note here that anytime we are working with temperature when using our gas laws, we need to use what we call an absolute scale, a scale that does not take on negative values. For this, we will use the Kelvin scale, in which Kelvin is going to be equal to our degrees C plus 273.15. At the Kelvin scale, absolute zero, or 0 Kelvin, is the temperature at which all molecular motion theoretically would stop. And so again, I can't stress enough that anytime you are using gas law and talking about temperature, you always must convert that temperature to Kelvin. When doing so, be mindful of your significant digits. Remember that when we're adding and subtracting, our significant digits are determined by how far past the decimal point our least accurate measurement goes. In this top case, we have our initial measurement in degrees C, which only goes to the 10th place. Our conversion to Kelvin goes out to the 100th place. And so our final measurement is going to only go to the 10th place because that's our least accurate number involved in our calculation. And so we would go to 298.2. In this example here of converting back to degrees C from Kelvin, we have a temperature of 323 Kelvin. We're going to subtract our 273.15. Our least accurate measurement only goes to the ones place. And so our answer would also go to the ones place. Also, just note here that when we're talking in terms of Kelvin, Kelvin is not based on a degree scale. And so we do have 25.0 degrees Celsius, yet that will be 298.2 Kelvin. It is incorrect to say degrees Kelvin. Kelvin is not based on a degree scale. And so this brings us back to our actual mathematical relationship of Charles's law, which tells us that V1 over T1 will equal V2 over T2. Just like in Boyle's law, problems involving Charles's law will often involve two sets of conditions, and you will be looking to explore what happens to one of the parameters when one of those conditions is changed. For example, here we have a 5 milliliter sample of carbon dioxide gas, which is enclosed in a syringe at 22 degrees Celsius. If we then take the syringe and immerse it into an ice bath at 0 degrees C, we want to know what the new volume will be, assuming that our pressure is going to be held constant. And so if we start to write down the information that we're given, our initial volume is 5.0 milliliters. Our initial temperature is 22 degrees C, which is equal to 295.15 Kelvin. I would get into this habit of automatically just converting your temperatures over to Kelvin first thing. We also know T2 at 0 degrees C, which is equal to 273.15 Kelvin. Our unknown that we are looking for is going to be V2. And so we set up our Charles's law relationship, V1 over T1 equals V2 over T2. We're looking for V2, and so solving for V2 gives us V1 times T2 all divided by T1. And now we can just plug in our numbers for that. And then we find that our new volume is then equal to 4.6 milliliters. And now, if we think about if our answer makes sense, in this instance, our temperature decreased, We said that temperature and volume are directly proportional to each other, so our volume should have decreased as well. And in fact, we went from a measurement of 5 milliliters to a measurement of 4.6. So Charles's law held true. In this example, we have a syringe containing 12 milliliters of air at 25 degrees C, which is placed into a sterilizer and heated up. The syringe is sealed, but the plunger can move, so the volume can change. After being sterilized, the new volume of air is 15 milliliters, and we want to know what the temperature was that was used in the sterilization process. And so we know our initial volume of 12.0 milliliters. We know our initial temperature at 25 degrees C, or 298.15 Kelvin. And we know our final volume of 15 milliliters. And so, setting up our Charles's law expression, V1 over T1 equals V2 over T2. Here, we want to solve for T2. Make sure with problems where you're solving for a temperature that you are using the algebra correctly. Our T2 is in the denominator here, and so we need to bring that up to our numerator. What I would recommend, especially if you're a little bit fuzzier with some of your algebra skills, is first to cross multiply. And so when we cross multiply, we're going to multiply V1 times T2 and T2 times V2 and set those equal to each other. Now, T2 is up into our numerator, so to speak, and it makes it very easy for us to now solve for T2. T2 will equal T1 V2 all over V1. And now we simply plug those numbers in, which gives us a value of 373 Kelvin. We then convert that back to Celsius, subtracting 273.15 for a temperature of 100 degrees C. And so again, if we think about our answer, in this case, our volume increased, and we said that volume and temperature are directly proportional to each other, and so our temperature should have increased as well. And it did, from 25 degrees C to 100 degrees C. Another relationship to look at is known as the Gay-Lussac law. This law investigates the relationship between pressure and temperature, assuming that volume remains constant. And so if we think of our balloon at a certain volume, with its certain number of collisions on the inside of the container, assuming that this volume remains constant, if we increase this temperature and we increase the motion of our particles, then it only makes sense that that is going to result in more collisions with the side of our container, leading us to say that pressure and temperature are directly proportional to each other, giving us a mathematical relationship of P1 over T1 equals P2 over T2. And you would solve these problems much in the same way that you would solve a Charles's law problem. It's not often, however, that only one of our parameters will change. For instance, if we are talking about taking a balloon, maybe from sea level, up to an elevation of 5,000 feet, then we will not only have a change in pressure, but we will likely have an accompanying change in temperature as well. For problems like this, where we're going to maybe change two parameters, we can combine Boyles, Charles, and the Gay-Lussac law into the combined gas law. Combining all of these gives us a relationship of P1 V1 all over T1 equals P2 V2 over T2. This now gives us a way to explore what happens perhaps to volume if both pressure and temperature change. And so here we have an example just like that. We have an inflated balloon with a volume of 6 liters, And at sea level, which means its pressure is going to be 1 atm, that balloon is allowed to ascend in altitude until it now reaches a pressure of 0.45 atm, and the temperature is going to go from 22 degrees C initially down to negative 21 degrees C. We want to know the final volume of that balloon at the new altitude. And so let's convert our temperatures to Kelvin immediately, and then we can set up our combined gas law relationship. P1V1 all over T1 equals P2V2 all over T2. We want to solve for V2, and so algebraically we need to multiply both sides by T2, and then we need to divide both sides by P2, and that will give us our new volume. Plugging in those numbers gives us a new volume of 11.34 liters. Technically, correcting for significant digits, we only have one significant digit in our initial pressure value, and so our answer would have to be then reported as 10 liters. Here we have another example in which we have a sample of carbon dioxide in a flask, initially with a volume of 25 milliliters, and at a temperature of 20.5 degrees C, or 293.65 Kelvin, and an initial pressure of 436.5 millimeters mercury. We want to know the volume of another flask, so we move the CO2 over to that flask, which has a pressure of 94.3 millimeters mercury at a temperature of 24.5 degrees C, or 297.65 Kelvin. And so we're looking for the volume of our new flask. And so again, we set up our combined gas law relationship. We need to solve for V2. And then we can plug in our numbers, telling us that the volume in flask B is 117 milliliters. Avogadro, yes, that Avogadro, who the famous number is named for, did a lot of his work with gases. Some of the work that he did involved finding the relationship between volume and the amount of a gas. One of the things that he found was that equal amounts of gases in moles at the same temperature and pressure occupy equal volumes. In other words, the volume of a gas will be directly proportional to the number of moles of that gas. And so if we have twice as much volume, as long as pressure and temperature remain the same, that means we will have twice as many molecules of that gas. And so to state that again, equal volumes of gases at the same temperature and pressure will contain equal numbers of molecules. This is regardless of the identity of the gas. In other words, for instance, at STP, 1 mole of hydrogen gas will occupy 22.4 liters. Also at STP, 1 mole of radon, which is much, much larger, will also occupy 22.4 liters. That 22.4 liters is an important number for us. That is the molar volume of a gas. At standard temperature and pressure, which is 273 Kelvin or 0 degrees C, and 1 atm of pressure, all gases will occupy 22.41 liters. Again, regardless of the identity of the gas. This also leads us to identify what we do call a standard set of conditions for gases. Standard temperature and pressure is defined, as said earlier, as 273 Kelvin and 1 atm. Here in this example, we have a scuba tank with a volume of 8 liters. And we're told that it contains air at 140 atm of pressure at 20 degrees Celsius. Here we want to know what the volume is going to be at STP. We defined STP as having a pressure of 1 atm and 273 Kelvin. And so we can use our combined gas law, giving us a value of 1.0 times 10 to the third liters of air. For one thing, this tells us just how compressible gases can really be. We can take what would normally be 1,000 liters of air and compress that down using high pressure down to simply 8 liters so that a scuba diver is able to take that down below with them. Now from here, we also want to know how many moles of the gas are going to be present. For this, we can use our molar volume. We said that at STP, which is the conditions we're at now with our 1,000 liters, 1 mole of a gas will be equal to 22.41 liters. And so we can simply use that as a conversion factor. This 1.0 times 10 to the third liters that we have times 1 mole per 22.41 liters gives us 0.0465 moles of air. Now we won't always be at STP, however, and maybe wanting to know our number of moles. For problems like this, or for problems when we're looking at one set of conditions rather than two different sets, we can use what we call the ideal gas law. The ideal gas law relates for us all of the different factors that we said influence the properties of a gas. We have our pressure times our volume will be equal to the number of moles times our gas constant R times our temperature in Kelvin. This gas constant R will always be equal to 0.08206 as long as your volume is in liters, your pressure is in atm, and your temperature is in Kelvin. And so this leads us to the ideal gas law of PV equals nRT. And so some things to remember when using the ideal gas law. Like with all gas law temperature calculations, you must always convert to Kelvin. If you are given an amount in grams, then you can use your molecular weight to convert that to moles. And always just make sure that you're using the correct units of R. You will have to have liters, atm, mole, and Kelvin in order to use that 0.08206 number. There may be different ways that you will have to use the ideal gas law. Perhaps one of the more common is to simply determine one of the variables, either pressure, volume, temperature, or number of moles, if you're given the other three in some way. You may need to determine new values of pressure, volume, temperature, or moles after the gas undergoes some sort of change. You could possibly use the ideal gas law in stoichiometry problems. Since this gives us a way to find the number of moles of a gas, you may be given the pressure, volume, and temperature and asked to find moles in some sort of reaction. And you can also use the ideal gas law to find the density of a gas or the molar mass. Here, I just point out some of the different values that R can have depending on your units. Again, the one that you will be using most often for this course is 0.08206, as long as you are using the correct units. Here we have an example of a gas which is in a 250 milliliter flask at a pressure of 1.3 atm and a temperature of 31 degrees C. And we want to know how many moles of that gas are present. And so we're going to use our ideal gas law, PV equals nRT. We want to solve for N, and so N is going to equal PV divided by RT. And so we can simply plug in our numbers. Our pressure of 1.3 atm, our volume of 250 milliliters, the ideal gas constant, 0.08206, times our temperature. To find that we have 13 moles of the gas present. Let's look at a real-life example. Tennis balls are filled with either air or nitrogen gas to a pressure above atmospheric pressure in order to increase their bounce. In this particular case, we have a tennis ball with a volume of 144 cms cubed, which is equal to 144 milliliters. It contains 0.33 grams of N2, which we will then have to convert over to moles. .0118 moles. And we have the temperature equal to 24 degrees C. And so we just use our ideal gas law in order to solve for pressure, which will be equal to nRT over V. And then we can simply plug in our numbers and solve for the pressure, giving us then a pressure of 2.0 atm and giving our tennis balls a nice little bounce. And so, we explored several different gas laws here. We looked at either comparing two different conditions, a before and after, so to speak, in which we would use Boyles, Charles, the Gay-Lussac, or the combined gas law, or possibly we just have one point in time where we're trying to solve for one of the parameters, in which case we would use the ideal gas law. And here we see a way where we can actually calculate the density of a gas. If we remember that the moles of any gas are going to be equal to our mass divided by our molecular weight, and we can take the ideal gas law, PV equals nRT, and substitute the mass divided by the molecular weight in for our value of N. If we rearrange this equation, that gets us to M over V equals pressure times our molecular weight divided by RT. And remember that M over V is simply equal to density. So as long as we know the pressure and we know the identity of a gas, so we can find the molecular weight, we can multiply those, divide by R times our temperature, in order to find our density. And so here we want to know what the density of oxygen is at STP. And so we said that M over V, our density, will be equal to pressure times our molecular weight divided by RT. And so we substitute all of those numbers in. At STP, we're at 1 atm of pressure. Our molecular weight of oxygen is 32 grams per mole. All over R times at STP, 0 degrees C is 273.15 Kelvin, for a value of 1.428 grams per liter, which is the density of oxygen at STP. So in this video, we explored many of the different properties of gases and how those properties can then translate into several gas laws, which allow us to calculate some of the properties of gases at different conditions. I hope you found this video helpful. As always, there is more practice on the website, and feel free to either come see me or go to a past session for some additional help.